You may have heard that quantum mechanics is weird and cannot be understood. Well, what if I told you that some of that weirdness can be found in classical mechanics as well? That we can develop classical analogues of the uncertainty principle of diffraction or entanglement. And all that you need is one simple trick. Follow the third law of thermodynamics. Well, let's see what I mean. So let's start with one of the hallmarks of quantum mechanics, the uncertainty principle. This limits the precision of the preparation in a way that the standard deviation on the position times the standard deviation on momentum has to be greater or equal to h bar over 2. And again, I want to stress that the uncertainty is on preparation, not on measurement. The uncertainty is there before we have the measurement. It's not a consequence of the measurement. You really can't have states where position and momentum are better specified than this. So this is really a statement about what quantum states are, not how we can measure them. So this is what we have in quantum mechanics, and in classical mechanics, in principle, there is no limit to the uncertainty. We can have a rectangular uniform distribution, and we can imagine to shrink the uncertainty as small as we want. In the limit, we can imagine shrinking this to a point. So while this is true in classical mechanics, in principle, there is a limit that comes out from thermodynamics when we are doing classical statistical mechanics. And the limit comes in the form of the third law that tells us that the entropy can't be negative, that it has a lower bound. And so if we take our probability distribution and if we calculate the entropy, the Gibbs-Shannon entropy, that's minus kb, the integral of rho log rho. And if we make this calculation with this particular distribution, we find that we have kb logarithm of delta x and delta p. And the logarithm is a monotone function, so we can imagine of shrinking delta x and delta p. At some point we are going to cross zero and we're going to have a negative entropy, and in principle we have no lower bound on the entropy and we can get it as arbitrarily negative as we want. And this, of course, is a problem. And it's a problem that is technically not in classical statistical mechanics by itself, but when we have classical mechanics with thermodynamics. So the idea is that we're going to take classical statistical mechanics, we're going to take ideas from there, that the states are distributions over phase space, and that the entropy is given by the Shannon-Gibbs entropy. And we are going to add the elements of thermodynamics, meaning the entropy has a lower bound. And we're going to pretend that we do not know that quantum mechanics even exists. And just by having these two things together, we are going to see that there are some classical analogues of quantum mechanics in classical mechanics plus thermodynamics. So, for example, let's go back to our expression of the entropy. Well, one of the things that we see here is that we have a rho or a delta x delta p inside a logarithm, and that's problematic because this has units of position times momentum, and this has units of probability over areas of position momentum. And the logarithm can only take a dimensionless quantity. So we should fix these expression first so that we have units that make sense. So how do we do that? Well, as we said before, we can shrink a uniform distribution, and while we're shrinking, we are going to decrease the entropy more and more. At some point, we are going to hit a uniform distribution that has zero entropy. And that uniform distribution is going to have a support, an area over which that distribution is defined. So we're going to define h as a constant to be the area of a region that corresponds to the zero entropy. Then we can modify this expression to multiply rho by h. So now we have units of position of momentum divided by units of position of momentum for the density, probability density. And if we do the calculation, we're going to have a logarithm of delta x delta p over h. So it's going to be the area in units of h that is going to give us the entropy. And note that if our distribution is over an area of h, h over h is going to give it 1, and logarithm of 1 is 0, so we are going to have that uniform distribution over areas of h give us a 0 entropy. So this is what we want. And again, I want to stress that here is H is not taken from quantum mechanics, because we don't know that quantum mechanics exists, is defined by the third law, by the fact that we have a minimum of entropy. So we should really think of H coming from that. It's a thermodynamic quantity. In fact, the Planck constant H was introduced to fix problems in thermodynamics. And the other thing that I want to make sure that you understand, H is a lower limit. It's not that phase space comes in multiple of H. So we can have a uniform distribution of area over an area of 1.3 H. That's not the issue. It's the minimum. We can't go below that. So really, in the old quantum mechanics, people were thinking that you have some kind of discretization of phase space. The phase space comes in cells of size H. And that's not what we're saying. It's something completely different. What we're saying is that the areas comes with a lower bound. And you can have the areas wherever. You can have them as big and as complicated as you want. The important thing is that they can't be smaller than H for a uniform distribution. Okay, so now we have some kind of scale that sets essentially the scale for the precision that we can have in phase space. And now we're asking, what is the distribution that minimizes the uncertainty at a given entropy? So far we said that we have uniform distribution over H, an area of H, but we haven't said whether those are actually the ones that minimize the uncertainty between position and momentum. It turns out that they are not. The distribution that minimizes the uncertainty at a given entropy, so we fix entropy at 0, we look for the distribution that minimizes the uncertainty, well, that distribution is the Gaussian, is this distribution. And if we calculate the entropy, as we did it before, we find that the entropy for a Gaussian depends on the standard deviation of position and momentum in the following way. It's going to be kb logarithm of 2 pi e sigma x sigma p over h. And now we want this entropy to be greater or equal to 0. And if the entropy is equal to 0, then the logarithm has to be the logarithm of 1. So this quantity has to be greater than 1. And therefore, sigma x sigma p is going to have to be greater or equal to h over 2 pi e. And h over 2 pi is h bar. So this has to be greater or equals to h bar over e. And this is very similar to what we have in quantum mechanics. The difference is that in quantum mechanics we have a 2, and in this classical version of the limits we have e, which is a little bit greater than 2. So we have that every classical distribution with non-negative entropy satisfies this inequality, and the equality holds for independent Gaussian, when we have Gaussians, a product of two Gaussian in position and momentum, and every quantum state which has non-negative entropy, because quantum states have 0 entropy or more, satisfies a similar expression, and again the equality holds for Gaussian wave packets. To understand this a little bit better, we can look at this plot. On the x-axis, we have the uncertainty measured in units of h bar, and on the vertical axis, we have the entropy. So we have a relationship between the uncertainty and the entropy. And this is the logarithm of the uncertainty. So this is the entropy for a Gaussian distribution based on the uncertainty delta x and delta p. So this region is excluded. We're never going to have a distribution that has an entropy that is greater than what a Gaussian has for a particular value of the uncertainty. Underneath, instead, we have the region of distributions that we can potentially have, except that we have to exclude these because of the third law of thermodynamics. We can't have negative entropy. In red, instead, we have the entropy for Gaussians in quantum mechanics. And what you see is that, even just above 1/2, the two plots are basically indistinguishable. The entropy of classical Gaussian or quantum Gaussians are basically the same. But then when you start being in this region, you see that they diverge, and the one for quantum mechanics hits here the graph at 1/2, which is the uncertainty principle in quantum mechanics, while the classical mechanics one goes a little bit further in, and this is where we have the h bar over e. So why is there that difference? Well, as I said, in classical mechanics you reach this point because you have independent distribution in position and in momentum. And in quantum mechanics, because you really can't define distribution in position and momentum, you can't really have independent distribution in position and momentum. So there is kind of a correlation in quantum mechanics, and the uncertainty then it's a little bit less because these distributions are they have a correlation. Okay, so we have seen that there is a classical uncertainty principle, and now we want to see if there are other classical effects that we can find that are kind of like quantum mechanics. So let's look at diffraction. So we have a wave that comes in from the left, and then there is an obstacle with a slit. The wave does not just go through it straight, but it bends around the corner. And the smaller the opening, the more it's gonna bend, the more it's gonna go around that corner. And what happens in quantum mechanics is that particles do this as well. And so we have this phenomenon of diffraction for quantum particles. So can we find a similar thing in classical mechanics given what we have seen before? Well, again, suppose that now we don't really have a wave, but we have an incoming distribution that has zero entropy, and the spread in momentum is very narrow, and it's spread across zero because this is the momentum in the x direction. So we're not going to go up, or we're not going to go down, we're just going to go in this direction. And of course we have a minimum spread, the overall spread, which is h. So we're going to have a big spread in x and very small spread in momentum. Now we go through the slit, and what's going to happen is that in principle the slit is going to chop our distribution in space and constrain into a very small distribution in position. But we can't have an entropy lower than zero. And so we need to restretch our distribution in terms of the momentum. So the distribution that comes out of the slit must have a bigger spread in momentum. But if it has a bigger spread in momentum, there are parts that are going to go up and parts that are going to go down. And therefore, it's going to diverge, it's going to diffract. And suppose now we make the opening smaller, well, that will constrain the final distribution to have a spread in position even smaller, and therefore a spread in momentum even bigger, and therefore there is going to be more of the distribution that goes up and more of the distribution that goes down. So this is kind of similar, it is kind of a classical effect for diffraction. And again, obviously, this is all qualitative. I don't want you to start thinking, oh, let's go and make prediction. I mean, this is just very hodgepodge. And in fact, there is no single way to spread the distribution. We only know that the distribution has to be constrained in X. We don't know what's gonna do in P. And if one look at the diffraction from a single slit, you're going to also see that there are these extra peaks because there is some sort of wave-like pattern. And of course, the argument so far does not give those extra peaks, and I'm not going to even try to go and justify those extra peaks. But the point is that if we have classical mechanics and we assume some type of lower entropy bound given by the third law, then we are going to have some type of diffraction. So it's not completely out of the blue that we would have some effect like that. Okay, we talked about diffraction. What about interference? Can we get interference? Well, we're not going to get an interference pattern with things that go up and down for the same reason that we saw before, but we can think of interference like this. That if we have two slits open, well, this is not the same as having one slit open at a time, right? The idea that the particle goes through both slits and not just one. Well, this idea is something that we can recover. Because in fact, again, imagine that we have our incoming distribution, that it has very narrow distribution in momentum and very wide distribution in position. It goes through the two slits, right? And now the distribution has to be constrained into these two intervals of position. And again, the total area has to be h. But it has to be the total area. If we only had one slit, well, all the spread would have to be happening in the upper part, and if we had only the slit below, we would have all the spread happening in the lower part. And so we now put them together, we actually have a spread of 2h. And so this gives us two different cases. Both slits open gives us one case, but if we open them one at a time, we would be able to tell that we have some different distribution. And again, this is all qualitative. There is no single wave of the spread of distribution. We are not going to get the interferent pattern. But again, this tells us something that I think is still insightful even in quantum mechanics. This entropy constraint, the zero entropy constraint, it's a global constraint. It's something that tells us, and it's about the whole distribution, not parts of the distribution. And so you get a different answer if both slits are open or not, because the entropy is a global constraint. And again, this might give you some insight of why we have this quantum effect in a way that it's a little bit more intuitive and physically justified. Okay, let's proceed to another quantum effect, entanglement. What is entanglement? Well, entanglement means that if we have the full specification of a composite system, we have a composite system that is in a pure state, that does not always give us a full specification of the components. So we have some states in which the full system is well defined, but the components are not well defined. They are in a mixed state. And so the idea in quantum mechanics is that composite system can access more states than those accessible by the two systems independently. So can we get something like that in classical mechanics? Well, in classical mechanics, if I have a perfectly prepared composite system and a perfectly specified composite system, then I'm going to determine both systems. I have a point here, and this point is going to tell us exactly what A and B are doing. But this assumes that, again, we can make a perfectly prepared system, a system with absolutely no uncertainty. And so, what if we can only prepare a system up to a zero entropy bound? Well, in that case, what happens is that we're going to have a joint distribution, and again, we assume it for simplicity that this is a uniform distribution, and then we are going to have marginals, and the marginals are going to be integrating the joint distribution over the average system. So here we have rho A, and the marginal for A is given by the integration of the joint over B. And in this setting, in this classical setting, the joint entropy, so the entropy of the composite system, is equal to the entropy of the marginals minus what is called the mutual entropy or mutual information. And this is defined to be the integral of rho AB, the joint distribution, with the logarithm of the joint divided the product of the marginals. And this has to be greater or equal to 0. And you see that this is going to be 0 only when the argument of the logarithm is going to be 1. And this is 1 exactly when rho AB is equal to the product of rho A, rho B. So when we have statistical independence. So now let's introduce our zero entropy constraint and let's see what happens. So we're going to assume that the joint system, the composite system, is perfectly specified, which means it's specified, it's a state with zero entropy. So this part is 0. Now, let's assume that we have statistical independence. That is, the mutual entropy is going to be 0. Well, this is going to be 0, this has to be 0, and the sum of the entropy of the two marginal have to be 0, but the entropy can only be 0 or greater, therefore both the entropy of the marginal have to be 0. So if we have a perfectly specified joint state, and we assume that we have statistical independence, then it is true that both states are perfectly specified. But suppose now that we have a mutual entropy, that these are not independent, so that this number now it's negative. You have minus something. And for this to be 0, one of the two has to be greater than 0. So if we have some mutual entropy, if we don't have statistical independence, we are going to have a joint system at 0 that is perfectly specified, but the individual systems are not. And this is just a correlation. So we can imagine that, again, we have our spread for zero entropy, but it's not rectangular this time, it's spread diagonally. And so we're introducing a correlation that makes the spread over the two systems increase. Also in quantum mechanics, you have a perfectly specified composite system and perfectly specified part when the joint is the product of the marginal, which is exactly what we have for statistical dependence. So entanglement is just a correlation, and this comes out again because we have this limit of zero entropy, which tells us that not all ensembles at zero entropy are the product of ensembles at zero entropies, because sometimes we have correlations and we don't have products. So now the composite systems, even in these classical settings, can access more states than those accessible by the two systems independently. Now, regarding entanglement, there is another thing that it's in quantum mechanics. It's the idea of the purification of a mixed state. The idea that if we have any quantum statistical mixture that's going to be written in terms of a density operator, well, this statistical mixture can be understood and can be expressed as the marginal on an entangled composite system. So you can always think of all the statistical distribution as being something that it's entangled with something else. So can we do the same thing in classical mechanics? Again, if we assume a perfectly prepared composite system, no, we can't do it. But what happens if we put the limit of zero entropy? Well, again, we have the expression that we had before, that the entropy of the joint is equal to the sum of the entropy of the marginal minus this mutual entropy. So we can imagine that we start with a distribution rho A where the entropy is greater than zero, so that the spread over A is great. And now we're going to find a rho B that has an entropy that it's minus the entropy of rho A. So for now we put in a distribution on B that has negative entropy. And so, for example, you could get a Gaussian, modulate the variance, and you're going to get exactly one that matches the correct entropy. And now we take the product of the two marginals, and now we have a joint distribution that is the product of rho A and rho B. And of course, this is going to have an entropy that is zero, because in this case, A and B are independent, so the mutual information is zero, and therefore we just have the sum, but the entropy of B is minus the entropy of A, so the joint is zero. Of course, this does not work because we have a negative entropy and we need the entropy to be positive, so what do? Well, we can introduce a correlation, and we can do it essentially by shifting these distribution along A. And if we do that, the distribution along A remains exactly the same, and we're going to spread the distribution along B while not changing the entropy of the joint. So more mathematically, the joint distribution is equal to the product of the distribution on A times the distribution of B minus f of A, such that when we do the integral on B, well, by changing variable, this goes away, and we just have the distribution of A. So yes, we can purify even classical states if we again understand that pure states are not perfectly prepared states, but states prepared up to zero entropy. So to recap, if we make this parallel that a quantum pure states corresponds to a classical distribution with zero entropy, then we find all these classical analogues of quantum mechanics. We have an uncertainty principle because the entropy bounds the uncertainty, and as we saw, the graph is very similar, except that for low entropy there is going to be a difference, and we're going to have a bound of h bar over E instead of h bar over 2. We can get some similar ideas of diffraction, because when we are constraining position, then it means that we're going to expand the distribution of momentum, leading things to go up and down while they go through a slit. And we're going to have some type of analog of the interference, because if we make the distribution, the single distribution, go through two slits or one slit, the way that this distribution will spread will have to be different in the two cases. And then we saw that we can have a notion of entanglement, because zero entropy on the joint might still give you positive entropy on the marginal if you have a correlation. So entanglement is just a correlation. And we can purify a system, meaning that we can think of any distribution, a classical distribution that have entropies greater than 0, we can still think it as coming from a joint that has 0 entropy. So what's the point of all of this? That we have to go around trying to find these effects in classical mechanics? Not at all. The point of all of this is to show that quantum mechanics is not so unreasonable as people make it out to be. There is always this push to show how quantum mechanics is mysterious and counterintuitive, and I think it's self-defeating, because if you want to understand something, well, it needs to be intuitive and it needs to be explained with simple ideas. And as long as we use hidden variables and parallel world and consciousness that causes the wave function collapse, I think we're going to understand nothing. So what I hope you saw here is that there is a way to use simple concepts, things that we have in normal physics, and show these effects are already there. We don't need to invoke a very strange thing. And you might have been surprised. I was also surprised to find this effect once I started looking. And the fact that I was surprised, it meant I didn't really understand classical mechanics. I didn't really understand classical statistical mechanics and the importance of the entropy in all of this. So it's not that there is this big, weird, mysterious theory called quantum mechanics that we don't understand. It's that we really don't understand simple things in all of physics. And I think that's the problem that we have at the foundations of physics. All these results are part of my research program called Assumptions of Physics, where I try to go and look for all these assumptions that are embedded in all the different theory, classical mechanics and quantum mechanics, and understand what is the difference between them and what is actually the same. And if you're interested in these sort of things, well, subscribe to the channel. There is going to be a link in the description to the wider project that you can see all that we publish, and you can find the presentation that we've given. And if you're interested to the more cutting edge of the discussion, well, I also have another channel in which I'm going to try to do open research on YouTube, because as you see in this video, we really need to put ideas together from a lot of different areas. So thank you for the attention and see you next time.